I wanted to give you another example of using kinematic equations to answer interesting questions. But this time, I wanted to show you a problem that uses natural language such as you might get from a client as an engineer, or you might encounter on a job. In this example, we're trying to design a runway for a small airport. This is the kind of thing you might encounter as a civil engineer. And as you read through this, it says you have an airplane that must reach a speed of 27.8 meters per second in order for it to take off. And this little airplane can accelerate at 2 meters per second squared. Your runway that you've got is 150 meters long. Can this airplane use your runway for takeoff? Now, the first thing you should notice is this question doesn't ask us for T1 or X naught, right? It uses natural language. This is the kind of problem that you would encounter in a real job. In fact, even at this stage, we've done a lot of the work for you. We told you what the speed the airplane had to reach. We told you what the acceleration of the airplane was. These would be the kind of details that as an engineer, you would have to go and look up the technical specifications of the airplane. You would have to research and find out. But we want to be able to start you on that path. And so we want to look at how can we answer these kinds of natural questions. And the first thing we have to be able to do is translate the natural language into a physics question that we can then use our physics tools to solve. So what does it mean for this airplane to take off? Well, we said it has to reach a speed of 27.8 meters per second. That means that as my airplane comes running down the runway, by the time it gets to the end, my velocity had better be 27.8 meters per second, or I'm going to run off the end of your runway. Now, there are a couple of different ways we could approach this problem, right? We could say, well, given that acceleration and that distance, what's going to be our velocity when we reach that point, and see if it's greater or less than 27.8 meters per second. Or we could take an alternative approach and say, well, given that I need to reach this velocity, how much distance do I need before I can reach that velocity, given that I have an acceleration of 2 meters per second squared? Either way will get us to the answer. But that has now let us translate this question, can my airplane use your runway to take off, into a question we can now answer. How much distance will I cover before I can reach 27.8 meters per second? So let's start off by just drawing a motion diagram so we can understand the general shape of the physics. I'm going to start at the beginning of my runway here. I'm going to accelerate at 2 meters per second. And I hope that by the time I reach the end of the runway, I'll have reached the velocity that I need. So we'd have a motion diagram that looks something like this. Note, we're not pulling up into the air yet. We're still moving in one dimension with an acceleration in this direction. I'm going to choose again that this be the positive direction so that my acceleration ends up being positive. My velocities, as you can see, will also end up being positive. So this way I don't have to worry too much about minus signs and making sure that all my signs are correct. I've set up my coordinate system to make the math easy. If we draw a picture, let's see. We have really two relevant points, where we start and where we end. So there's my airplane. This is where I start. I start at t0. At time, my initial time, at some initial position. Now, we weren't given any constraints on the start time or the starting position, and so I'm going to choose to set these equal to 0. That way we can make the math easy. The other thing we weren't given, we have to think about. We're going to start with some initial velocity. Well, what is the initial velocity of a plane sitting on the front of a runway? Well, of course, it's going to be 0 meters per second because this plane will be at rest. We haven't started moving yet. We know we're going to be accelerating, and we know that that acceleration is 2.00 meters per second squared. And at some later time, we're going to achieve our takeoff velocity. Right? This is the point where we would be able to fly off into the air. That'll happen at some later time and some later position. And we want to make sure that our velocity at that time and position is equal to 27.8 meters per second. Okay, but we don't know how long that's going to take, and we don't know how far away that will be. And again, remember, we need this value to be less than 150 meters in order for this airplane to be able to use my runway. That's the question we're ultimately trying to answer. Now we've drawn a picture that helps us see the shape of the physics. We've used our motion diagram to set up our coordinate systems and get us thinking along the right direction. Now we can begin to think about what our data is going to tell us. We've written down our known values. We've labeled our, selected some labels. We've also written down our unknown values. And so now let's look at our equations. Which ones will help us get to the answer that we want to know in one step? Of course, we have two unknowns really. We don't know our final time, and we don't know our final position. But ultimately, we don't care about our final time. We don't need to know what this is. What we're ultimately after is to find out what is our final position. And since we want to know our final position, let's ignore any of the equations that have time in them, because at least at this first pass, let's see if we can get there in one step. Again, we're always trying to go from known to unknown in one step if we can. It's not always possible, but if we can, that's what we want to do. All right. So ignoring all the answers with time, do we have something that involves our final position? Of course, this one, the second equation, doesn't have anything to do with final position. So while we might be able to find some information there, it's not useful. Let's look at this last equation. This last equation has a final velocity. We know that. Has an initial velocity. Hey, we know that as well. Has an acceleration, which we know. Has an initial position, which we know. And the only thing we don't know is our final position. And that's the value we want to know. So this is a good equation to use. If we write this down, we're going to end up with using our variables now instead of the equation variables, v1 squared equals v naught squared plus 2a x1 minus x naught. Thinking about what our values are, we already know that v naught, that's 0, and x naught, that's 0. So we are left with something that looks like v1 squared equals 2a x1, which we can solve for x1, and we get then x1 is just v1 squared over 2a. As always, before we go any further, we want to check and see if this is reasonable. Let's just check our units. We're going to have on the top a velocity squared, so meters squared per second squared. And on the bottom, we're going to have acceleration. Since we're dividing by acceleration, let's multiply by the reciprocal. We're going to have meters per second squared. We should hopefully come up with units of distance. And so let's see, second squared cancels with second squared, meters cancels with one factor of meter, and sure enough, we end up with units of distance. So our answer looks pretty reasonable. We should be able to, this should give us, at least will give us an answer in unit of length. When we put in our values, we find that x1 ends up being equal to about 193 meters. So we got a distance of 193 meters before we can reach our velocity of 27.8 meters per second. Unfortunately, now we have to go back and answer our question, really, right? We didn't care what x1 was. We just cared, could my airplane use your runway? And now we have to go back to our question. 193 meters, that is definitely larger than 150 meters, which is the length of my runway. So no, this airplane cannot use this runway. And I would either have to, runway. I would either have to redesign my runway to be a little bit longer, or I'd have to say, well, this class of airplane can't use this airport. They're going to have to go to another airport. We said there were two approaches for answering this question. Can this airplane use our runway to take off? The one we looked at was to determine what distance the plane travels before it reaches the takeoff velocity. Now I'd like you to use the problem-solving approach that we've discussed so far to determine what the plane's velocity will be when it reaches the end of the runway.